This paper, which has been nominated for the Best Paper Award, is titled Enforcing Policy Feasibility Constraints Through Differentiable Projection for Energy Optimization. This is from Carnegie Mellon University, and I believe Bingqing Chen would be the presenter. Quick bio, Bingqing Chen and Priya, one of the co-authors, are PhD students at Carnegie Mellon, working at the intersection of machine learning and energy system. Bingqing's research focuses on learning-based control to improve energy efficiency, and Priya's research explores ways to incorporate power system physics and other domain knowledge into machine learning models. And the emphasis overall is on climate change mitigation. So this will be a recorded talk, and I think let's go ahead and watch the recording.
Hi, everyone. My name is Priya Donti, and I'm a PhD student at Carnegie Mellon University. Today, I, along with my co-author Bingqing Chen, also of CMU, will be presenting our work on learning flexible neural network policies that nonetheless satisfy the hard constraints associated with the systems in which they operate. This is joint work with Kyri Baker, Zico Kolter, and Mario Bergés. The key motivation here is that energy systems today increasingly rely on autonomous control. So, for example, machine learning has proven to be a powerful tool for learning expressive autonomous controllers that are adaptive to real-time signals from the underlying system. A challenge, though, is that machine learning methods often struggle to enforce the physics or hard constraints associated with the systems in which they operate, and this can restrict their application in energy system settings. For example, in building HVAC settings, it's often important that any autonomous controllers satisfy occupants' thermal comfort constraints. And in distribution system control settings, failing to satisfy equipment and operational constraints can lead to critical failures and equipment degradation. So while machine learning methods are adaptive, they tend to struggle to enforce relevant constraints. On the other hand, traditional robust control methods that do satisfy these constraints often tend to be rigid and not adaptive to changes in the underlying system. So in this work, we present a method, PROF, that aims to get the best of both worlds by coupling a neural network-based policy with a constraint enforcement technique that is visible to the neural network. This allows our policy to be adaptive to the reality of the underlying system while enforcing that our actions are feasible. The basic idea is that we first use a neural network to output some candidate action. This candidate action may not be feasible, so we then project it onto a set of feasible actions so that the resultant action is feasible. And this is where the name of our method, PROF, comes from. It stands for projected feasibility. To construct the set of feasible actions that we use in our projection, we base it on a potentially time-dependent approximation of the underlying system, which can be constructed using domain knowledge, as we'll show in our experiments. Importantly, we construct the projection onto this set in a way that is differentiable, which I'll describe in more detail shortly. We then enact this projected feasible action that comes out of the projection layer upon our true system, and then we incur some associated cost. We then use that cost information to update our neural network by taking gradients of our cost with respect to the neural network parameters, and then using that information within a reinforcement learning or policy gradient method like PPO. Importantly, the gradients here flow through the differentiable projection operation, so the neural network can take the projection into account when adjusting its parameters, and this improves overall performance. So to explain this a bit further, I'll first step back a bit to give some background on neural networks and differentiable learning. So fundamentally, neural networks can be viewed as the composition of multiple functions, also known as layers, where the functions are generally nonlinear and parameterized, and they're differentiable. The nonlinearity of the functions allows the overall neural network to be extremely expressive, and the idea is that we can adjust the parameters of these functions to improve the quality of the output of the neural network given data. The functions all have to be differentiable because of the specific way in which we do this. In general, we put some inputs into the neural network, get some corresponding outputs, assess some cost on the outputs, and then calculate the gradients of this cost with respect to all neural network parameters. This is called backpropagation. We then adjust all the neural network parameters based on this gradient information via something like gradient descent. We then repeat this process iteratively over and over. So while most neural networks use standard sets of functions, things like ReLUs, sigmoids, convolutions, and so forth, there's recently been a lot of interest in enriching the set of functions that can be used to include implicit functions like optimization problems and physical equations. So this is the body of literature that we build upon in this particular work, the body of literature on implicit layers. So to give a bit more intuition on implicit layers, I'm going to use the example of the projection operation. So the projection operation entails taking some input and finding the point in some constraint set that is closest to that input. This operation can be written as an optimization problem, as shown on the slide. So just for simplicity for right now, let's consider the case where all the constraints are linear. We're projecting onto a linear constraint set. This optimization problem then becomes a convex quadratic program, and we can write down its KKT conditions, which in this case are necessary and sufficient to describe all optimal solutions of the problem. Given an optimal solution, which we can find using a standard quadratic programming solver, we can then use the implicit function theorem to differentiate through the KKT conditions at the solution, which looks something like the system on the slide. We can then rearrange this system and solve for any gradients we need of the inputs or parameters of the projection problem. I'm making a few simplifications here. For example, we seldom compute these specific gradients on the slide directly and instead compute their products with other terms in a way that reduces time and space complexity. But at a high level, this is what's going on. We write down the equilibrium or fixed point equations of the optimization problem and use the implicit function theorem to differentiate through them. One thing I'll note is that I've used the example of linear constraint sets here for simplicity, but we can actually do something like this for any convex constraint set, since there are methods available to differentiate through general convex projection problems. To bring this back to our prof method, this kind of differentiable projection is exactly what we use in the context of prof. We project the candidate actions from our neural network onto the feasible set using a differentiable projection layer. The reason we want to do this is because it means that the gradients can flow through the projection operation. That is, the neural network is aware that the projection has occurred and can take this information into account when adjusting its parameters. This can improve performance compared to a black box post hoc operation that isn't visible to the neural network. So to emphasize this point further, let's take a look at the gradients that the neural network gets in two scenarios where the projection is or isn't visible to it. So this is the scenario first where the projection is not visible to the neural network. What's shown on the slide is the gradient field for some illustrative example, where a constraint set is in purple. The red dot is the unconstrained optimal action in the top right corner. The red star is the constrained optimal action, which is the action we actually want to learn. And the cost represents the L2 distance of our current action from the unconstrained optimal action. This is a proxy for the real system cost, which doesn't tend to contain constraint information. In practice, we wouldn't know the optimal actions ahead of time, but this is just for illustration. The black arrows show the gradient of the cost with respect to the neural network. Again, in this case, where the neural network is not given any information about the projection. In this case, the gradients basically push the neural network towards the unconstrained action, in many cases away from the constrained optimal action, as you'll see in the top right of the diagram, and this isn't desirable. On the other hand, when we allow the neural network to see the projection, the gradients of the neural network are now incentivized to move towards the constrained optimal action, which is the action we actually want. External to the constraint set, you can see that the gradients actually sort of circle around towards the unconstrained optimum. And so to incentivize the gradients outside the constraint set to fully point inwards towards the constrained optimum, we actually add an auxiliary loss term that incentivizes the pre-projection actions to be close to post-projection actions. And we give more details on this in the paper. So to summarize, our method PROF entails, selecting a candidate action using a neural network, projecting this action in a differentiable manner onto a feasible, potentially approximate action set, and then backpropagating signals about the quality of this action through both the projection and the neural network. I'll now pass it off to Bingqing to talk about our experiments.
Thank you, Priya. In this work, we demonstrated PROF on two distinct applications. The first one is energy-efficient building operation. The objective is to conserve energy while satisfying occupants' thermal comfort requirements. The simulation testbed we use is a high-fidelity model of a 600 square meter multifunctional space on Carnegie Mellon campus. The system we're controlling is a hot water-based radiant heating system. Here, we control the supply water temperature through these hot water pipes to maintain the room temperature at a comfortable range. Grounded in this specific example, let me elaborate on how we construct the safe set with an approximate model. We define safe set as the set of all admissible actions that satisfy the end-use requirements and physical constraints. Thus here, for the safe set, we consider the building thermodynamics, the allowable action due to the physical limits of the system, and the thermal comfort requirements posed by the occupants. Here, we assume that the building dynamics can be locally linearized and thus modeled as a linear system. And the action we consider here is we consider action over a 3-hour planning horizon. The resulting safe set is convex, and thus we can use the differentiable projection layer as Priya described earlier. Now let's look at the PROF's behavior in more detail. Here I'm showing the time series over a 3-day time period at the very beginning of the learning phase. The top part of the figure shows state, that is the room temperature, and the bottom part of the figure shows action, that is the supply water temperature. The dead band, that is the comfortable temperature range, is shaded here in light blue, which varies depending on whether the space is occupied or unoccupied. And the unoccupied time period is shaded in light blue as shown here. We pre-train PROF by imitating a baseline proportional controller. The proportional controller reactively turns on heating when the space transitions from unoccupied to occupied. As a result, every morning there is a period of thermal comfort violation. Interestingly, the differentiable projection layer enforces PROF to preheat the environment so as to satisfy the thermal comfort requirement, even though this behavior is not present in the expert demonstration from the P controller. After learning for a month, again we are showing the time series over a 3-day period, PROF picked up an energy-saving strategy by maintaining temperature just above the lower limit of the allowable temperature. This behavior explains why PROF further conserved energy compared to other reinforcement learning agents, for instance NeuRL, as indicated by the dashed green line here. In a nutshell, PROF improved energy efficiency by 23.8% compared to the existing controller while maintaining a comparable level of thermal comfort. Furthermore, PROF improved energy efficiency by 10% and 4% respectively compared to other reinforcement learning agents evaluated in the same environment. Now, let me switch gear and describe our second application, inverter control, where the goal is to control the active and reactive injection from the inverters so as to satisfy the voltage constraints in the distribution network. For those of you who are not familiar, inverter is a piece of power electronics that connects distributed energy resources such as solar panel, wind turbine, and battery to the distribution network. As the penetration of renewable energy resources continue to grow, the grid of the future will become inverter dominated, which makes the study of this problem particularly important. The testbed we're using here is a standard IEEE test case, the 37-bus feeder system. The solar panels, all connected via inverters, are indicated by the green rectangles. It may be counterintuitive, but increasing penetration of renewable energy can introduce unintended challenges for grid operator. Let's take this as an example. The top part of the figure shows the available solar energy as measured in Sacramento, California at 1 second time step over the course of a week. Around noon, when the solar power injection from solar power is high, the voltage exceeds the allowable limit as indicated by the dashed black line here. Volt control is a control strategy that is recommended by IEEE standard. In comparison to the no control scenario, volt-VAR does alleviate the situation to some extent, but still incurs violation 22% of the time. In practice, instead of allowing the voltage to exceed system limit, what happens in practice is that the active solar generation will be curtailed in order to prevent broader impact to the network. Given this practical problem, comes our problem formulation, where the goal is to control the active and reactive power at each inverter in order to minimize the curtailment, that is the solar energy that is wasted, subject to system level and device level constraints. The system level constraint is that for each node in the system, the voltage should fall within the allowable limit, and there are additional constraints on individual inverters on what are the level of power they can output. And then we put everything together using a linearized model of the distribution network, using the method proposed by this paper listed here. A notable advantage of the method proposed by the paper is that it provides a bounded error for linearization. As a result, we can construct a safe set that is a strictly conservative under approximation of the true safe set. Now let's look at the behavior of PROF applied to the same problem. In addition to showing the available solar power and maximum voltage, we additionally also show the curtailed energy. First thing to note is that PROF, indicated by the light blue line, satisfied the voltage constraint 100% of the time, even though it started off with a randomly initialized neural network. In comparison to the optimal solution with respect to the same linearized grid model, PROF's behavior is barely distinguishable after half a day. That is to say, PROF learned to do as well as possible with it in its conservative safe set after learning safely for half a day. However, we do have to point out that due to the conservativeness of its safe set, Prof curtails more energy than the true optimal solution. But on the flip side, the ACOPF solution is extremely expensive to calculate. To calculate the ACOPF solution at 1 second interval over the course of a week, the wall clock time sequentially is also a week, which is not very acceptable. To summarize, Prof is a method that enforces convex operational constraint within neural policy. The result of the method is a powerful neural policy that can flexibly optimize performance on the true dynamics while satisfying the constraints. In the building control scenario, Prof outperforms other reinforcement learning agents while mostly maintaining temperature within the dead band. The violation only occurs when the control is already saturated. In the inverter control setting, Prof satisfies the constraint 100% of the time over more than 500,000 time steps. Despite all these advantages, we want to also point out the limitations in direction for future work. Firstly, we do assume that there exists an approximate model for us to construct the safe set. We also assume the safe set is static, that is, it is not updated with new observations. As future work will lift these restrictions so that we can simultaneously learn neural policy and the safe set. Finally, our vision for this work is to integrate domain knowledge in physical constraints into learning-based method. Particularly, we believe the ability to enforce these physical constraints is paramount for success in real-world application. And we hope our talk has inspired other researchers to further explore this line of research. This is the end of my presentation. Thank you for your time.
Great, thank you.
Hi, everyone.
Any questions? Any discussion points for Slack? Maybe I have just a couple of points, perhaps, just before we break. Is the thing about, I think Bingqing pointed out about the limitation of knowing this feasible projection set reasonably well a priori. Again, not sure how easy or difficult it is to estimate that, especially when conditions in the building can perhaps change, like the previous paper talked about. Lighting controls requirements can change and so on. One other aspect I thought was, if this set changes, then is it necessary for the agent to be retrained right from scratch, and potentially how long would it take that? And how feasible is this solution to run in an online manner, again, from a pure practical perspective? So perhaps some high-level thoughts here. Any other questions from the audience?
Hi, and this is Keshav here. Yeah, I mean, it's a bit disconcerting because we can't actually ask the question here.
Yes.
So I think we can just talk amongst ourselves, but even that is not useful. So perhaps we will need to be forced to just do it on Slack and see.
Yeah. In the hope that the authors watch the video, maybe.
Oh, I see.
They might lead or pick up some of these discussion points.
I mean, my comment was, this is like a very powerful technique, and the one point which I was curious about is for the second application, what the cost of OPF with constraints, what the computational cost was compared to actual OPF. So OPF is of course a very complex and expensive operation. I don't know the speed up. Perhaps the paper has that. I have to go look at that. But that would be a very interesting alternative to OPF.
Yeah. Okay. Any questions? Please post it on the Slack channel for this session. I think that comes to the brings to close this particular session. I hope you enjoyed all the 3 papers, and maybe at this point I will hand it back to the Zoom master. Thank you.
Thanks a lot, Arun. So I'll stop the recording now.